Hello there, and welcome to the Science for Sleep channel. Tonight we'll explore atoms that have existed for billions of years. These invisible architects of everything drift through space and time, carrying the memory of ancient stars, the birth of galaxies, and the slow turning of the cosmos. Most of what they are is empty space, yet they form the solidity of mountains, the flow of oceans, and the warmth of your own breathing body. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Just before we begin, if this helps you rest, consider liking and subscribing. One sleepy soul at a time. Now let's begin with atoms. The atoms in your body are billions of years old, formed inside ancient stars that exploded long before Earth existed. Think about that for a moment. The carbon in your skin, the iron in your blood, the calcium in your bones, all of it was once deep inside a star burning in the darkness of space. Those stars lived their lives, grew old, and then scattered their atoms across the galaxy in massive explosions. Slowly, over millions of years, clouds of those atoms drifted together, pulled by gravity, until they formed our sun, our planet, and eventually you. Every atom you carry has been on a journey longer than you can imagine, traveling through time and space, waiting patiently to become part of this moment where you rest and breathe. An atom is 99.9% empty space. If the nucleus at the center of an atom were the size of a small peanut sitting in the middle of a football stadium, the electrons would be tiny specks orbiting somewhere up in the highest seats. Everything solid around you, the bed beneath you, the walls of your room, even your own body, is mostly just emptiness held together by invisible forces. The atoms don't actually touch each other. They hover near one another, their electrons pushing away from other electrons, creating the sensation of solidity. It's strange to think that something so empty can feel so real. But that emptiness is part of what makes atoms so patient, so enduring, so capable of forming everything we know. You share atoms with every person who ever lived. The air you breathe out drifts away and mixes with the atmosphere. And eventually, those same atoms are breathed in by someone else, somewhere else, perhaps years from now. Scientists estimate that with every breath you take, you're likely inhaling atoms that were once inside Cleopatra, or Shakespeare, or a dinosaur that walked the earth millions of years ago. Atoms don't disappear, they just move from one place to another, one form to another, endlessly recycling through the world. The calcium that once made up an ancient seashell might now be part of your bones. The carbon that powered a tree in a prehistoric forest might now help your heartbeat. It connects us all across time in ways we rarely stop to consider. The hydrogen atoms in your body witnessed the birth of the universe. They formed just minutes after the Big Bang, 13.8 billion years ago, when the universe was unimaginably hot and dense. As it expanded and cooled, protons and electrons found each other and became the simplest atoms, hydrogen. Those same hydrogen atoms have been around ever since, drifting through space, becoming part of stars, planets, oceans, and living things. Some of the hydrogen in the water you drink this morning is older than the sun itself. It's been waiting all this time, patient and unchanged, to be part of your body for this brief moment before moving on to whatever comes next. Every breath you take contains atoms that were once part of stars across the Milky Way galaxy. Our sun is just one of hundreds of billions of stars in this galaxy, and many of those stars have already died, releasing their atoms into space. When you inhale, You're breathing in oxygen that was created in the core of a distant star, perhaps one that no longer exists. Those atoms traveled across light years of empty space, carried by stellar winds and supernova explosions, until they arrived here on Earth. They became part of our atmosphere, our oceans, our forests, and now, for just a few seconds, they're inside you, fueling your cells, keeping you alive. Then you breathe out, and they continue their journey. The gold atoms in wedding rings were created in the collision of two dead stars called neutron stars. Gold can't be made in ordinary stars, like our sun. They're not powerful enough. It takes the incredible violence of two neutron stars spiraling into each other, colliding in an explosion so bright it can be seen across the universe, to forge gold atoms. These collisions are rare, happening perhaps once every 100,000 years in a galaxy. The gold on your finger, or in a piece of jewelry, or in ancient treasure buried long ago, came from one of those distant, catastrophic events. It traveled through space, became part of Earth when our planet was forming, and waited billions of years in the ground until someone dug it up. That's how precious and ancient every gold atom truly is. Atoms are so small that 100 million of them lined up would measure only 1 centimeter. You can't see them with your eyes or even with regular microscopes. They're far too tiny. It takes special equipment like electron microscopes or scanning tunneling microscopes to even catch a glimpse of their shapes. Yet despite being so incredibly small, they make up everything. The chair you're sitting on contains trillions upon trillions of atoms, all bonded together. Your body contains about 7 octillion atoms. That's a 7 followed by 27 zeros. It's a number so large it's almost meaningless to us. But each one of those atoms is real, has its own history, and plays its own small role in making you who you are right now. The human body contains about 7 octillion atoms, and more than 98% of them are replaced every year. Your body is constantly taking in new atoms from the food you eat, the water you drink, the air you breathe, and releasing old atoms as waste. The atoms that made up your body a year ago are mostly gone now, scattered back into the world. Yet you remain yourself, your memories, your thoughts, your sense of who you are. They continue even as the physical atoms that make you are constantly being swapped out. It's like a river that looks the same, even though the water flowing through it is always new. You are a pattern, a process, rather than a fixed collection of matter. And that pattern persists while atoms drift in and out, each one playing its part before moving on. Electrons orbit atomic nuclei at speeds approaching 2,200 kilometers per second, faster than anything humans have built. They don't orbit the way planets orbit the sun, though. Instead, they exist in fuzzy clouds of probability around the nucleus, appearing and disappearing in different places so quickly that we can only describe where they're likely to be, never exactly where they are at any given moment. This strange behavior is part of quantum mechanics, the rules that govern the smallest things in the universe. But despite all that chaos and speed, atoms are remarkably stable. The electrons stay in their orbits, the nucleus holds together, and atoms can exist unchanged for billions of years. All that motion, all that energy is perfectly balanced. It's like a dancer spinning so fast they become a blur, yet never losing their balance. The carbon atoms in your body have been recycled through countless living things over billions of years. Plants, animals, bacteria, fungi, all the life that ever existed on Earth. Carbon is the foundation of all organic molecules, the backbone of DNA, proteins, fats, sugars. When a living thing dies, its carbon atoms are released back into the soil or the air. Plants absorb them and build new leaves. Animals eat those plants and build new bodies. When those animals die, the carbon returns to the earth again. The cycle never stops. Some of the carbon atoms in you right now might have once been part of a dinosaur, a fern in a prehistoric swamp, a fish in an ancient ocean, or a human who lived 1,000 years ago. Carbon connects all life across time, linking us to every living thing that came before and every living thing that will come after. The iron atoms in your blood were forged in the core of dying stars 5 billion years ago. Iron doesn't form easily. It requires enormous heat and pressure, the kind that only exists deep inside massive stars much larger than our sun. Over millions of years, those giant stars fuse lighter elements together, building heavier and heavier atoms in their cores until they created iron. And when those stars finally exhausted their fuel, they collapsed and exploded as supernovae, scattering all that iron across space. Eventually, some of those iron atoms drifted into the cloud of gas and dust that formed our solar system. They became part of Earth, settled into the ground, and billions of years later, you absorbed them from the food you ate. Now they flow through your veins, carrying oxygen to every cell in your body. The iron in your blood is stardust. Atoms are never destroyed. The same atoms that exist now have been here since shortly after the universe began. They can change form, bond with other atoms, break apart, and move from place to place, but they never simply vanish. The carbon atom in a tree leaf today might have been in the soil last year, in a worm before that, in a bird that ate the worm, in the air after the bird exhaled, and in rainwater before the tree absorbed it. Atoms are endlessly patient travelers, moving through the world without beginning or end. Nothing is ever truly lost. It just transforms into something else, waiting quietly for its next form, its next purpose. This endless recycling means that every atom has a history longer than we can imagine and a future that stretches forward just as far. A single human hair is about 500,000 carbon atoms wide. That's how incredibly small atoms are. If you could line up carbon atoms side by side across the width of one strand of your hair, you'd need 500,000 of them to reach from one edge to the other, and your hair is already so thin. Imagine how tiny each individual atom must be. Yet despite their size, atoms are not simple. Each one has a nucleus at its center, with electrons orbiting around it in complex patterns. They have structure, behavior, properties. They can bond with other atoms in specific ways. They can vibrate, absorb energy, release light. All of that complexity exists in something so small that billions of them would fit on the period at the end of the sentence. The calcium atoms in your bones may once have been part of ancient seashells or mountain limestone. Calcium moves through the world in slow cycles. Rain falls on mountains, dissolving tiny amounts of calcium from the rocks. That calcium washes down rivers into the ocean, where sea creatures use it to build their shells and skeletons. When those creatures die, their shells sink to the ocean floor and, over millions of years, are compressed into limestone rock. Then, much later, geological forces push that limestone up to form new mountains. The cycle begins again. Some of the calcium that makes your bones strong today might have been part of a cliff face, or a coral reef, or a shellfish in an ancient sea. It has been recycled through the earth for hundreds of millions of years, waiting for this moment to help you stand, move, and live. Atoms vibrate constantly, even at absolute zero temperature, in what physicists call zero-point energy. They never stop moving. Even when matter is cooled to the coldest possible temperature, where you might think everything would freeze completely still, atoms continue to vibrate. It's one of the strange rules of quantum mechanics. Particles can never be completely motionless. They always have some energy, some movement. This means the atoms in your body right now are humming with motion, oscillating back and forth in their bonds, creating a kind of invisible symphony. You can't feel it or see it, but at the smallest scale, everything is alive with motion. Even in the stillest moment, atoms are dancing. The atoms that make up solid objects are mostly empty space held together by invisible electromagnetic forces. When you touch a table, what you're really feeling is the electromagnetic repulsion between the electrons in your hand and the electrons in the table. The atoms themselves aren't actually touching. They hover near each other, pushing away with just enough force to feel solid. If atoms were truly pressed together with no space between them, matter would collapse into something unimaginably dense. Instead, atoms keep their distance, and that distance creates the world of shapes and textures we know. The sensation of touch is really just forces pushing against forces, emptiness against emptiness, held in perfect balance. Oxygen atoms in water molecules have cycled through clouds, oceans, and living bodies for billions of years. The water you drink today is ancient. Some of it fell as rain on dinosaurs. Some of it flowed through rivers that no longer exist. Some of it was locked in ice sheets that covered continents long ago. The oxygen atoms in that water have been part of countless organisms, plants that used it for photosynthesis, animals that drank it and breathed it, bacteria that broke it down and released it again. Water molecules are constantly moving through the hydrological cycle, evaporating from oceans, forming clouds, falling as rain, soaking into soil, flowing into rivers, returning to the sea. The oxygen atoms go along for the journey, patient and persistent, connecting all living things across time through the simple act of existing. Every atom heavier than hydrogen was created inside a star's nuclear furnace. Stars are atom factories. In their cores, hydrogen atoms smash together with such force that they fuse into helium, releasing enormous amounts of energy. This is what makes stars shine. As stars age, they begin fusing helium into heavier elements: carbon, oxygen, neon, magnesium. The most massive stars continue this process, creating silicon, sulfur, and eventually iron. But iron is as far as they can go. Fusing iron takes more energy than it releases, so when a massive star's core fills with iron, fusion stops. Without the outward pressure of fusion to balance gravity, the core collapses and the star explodes. That explosion creates the heaviest elements, gold, silver, uranium, and scatters all those atoms into space. Everything you see around you, everything you're made of, was built in stars. The universe creates no new atoms naturally. We're working with the same atomic inventory for billions of years. All the atoms that exist now were created either in the first few minutes after the Big Bang, when hydrogen and helium formed, or later inside stars, or in supernova explosions. Since then, no new atoms have been added to the universe through natural processes. The atoms just keep recycling, rearranging themselves into different combinations, different structures, different forms. The atoms in your body have been other things before you: stars, planets, rocks, oceans, plants, animals. And after you, they'll become other things again. Nothing is ever truly new. It's all just endlessly rearranged, endlessly reused, endlessly patient. Protons in atomic nuclei are made of even smaller particles, called quarks, held together by the strong nuclear force. When scientists first discovered protons, they thought they were fundamental particles that couldn't be divided further. But experiments revealed that protons are actually made of 3 quarks, 2 up quarks and 1 down quark. These quarks are bound together by particles called gluons, which carry the strong force, the most powerful force in nature. The strong force is what keeps the nucleus from flying apart, even though protons repel each other electrically. It only works at incredibly short distances, but within those distances, it's strong enough to hold matter together against enormous pressure. Without this strong force, atoms couldn't exist. Everything would come undone. An atom's nucleus contains 99.9% of its mass, but occupies only 1/trillionth of its volume. Almost all of an atom's weight is concentrated in that tiny center. If you could remove all the empty space from atoms and pack just the nuclei together, a single teaspoon of that material would weigh billions of tons. That's how dense atomic nuclei are. Yet in normal matter, the nuclei are so far apart, separated by vast regions of mostly empty space where electrons orbit, that matter remains light and manageable. The nucleus is incredibly small compared to the overall size of the atom. If the nucleus were the size of a marble, the whole atom would be as large as a football stadium. All that empty space is what gives atoms room to move, bond, and interact with each other in all the ways that create the world we know. Atoms bond with other atoms by sharing or exchanging electrons in their outer shells. This is how molecules form. Atoms want to have full outer electron shells because that makes them stable. Some atoms have extra electrons they're willing to share or give away. Others have spaces in their outer shells where they can accept electrons. When atoms come together, they can share electrons between them, creating what's called a covalent bond, or they can transfer electrons completely from one atom to another, creating an ionic bond. These bonds hold atoms together in specific arrangements, creating everything from water molecules to complex proteins. The way atoms bond determines the properties of the substance they form, whether it's hard or soft, liquid or solid, transparent or opaque. Chemistry is really just the story of how atoms connect with each other. The electromagnetic force between electrons and the nucleus is what gives matter its solidity. You might think solid objects are solid because their atoms are tightly packed together, touching each other. But atoms never actually touch. What makes a table feel solid when you press your hand against it is the electromagnetic repulsion between the electrons in your hand and the electrons in the table. Both sets of electrons have negative charges, and negative charges repel each other. When you push down, the electrons push back, with exactly enough force to resist your hand. That resistance is what we experience as solidity. If electromagnetic forces suddenly disappeared, matter as we know it would collapse. Everything would lose its shape, its texture, its ability to resist pressure. The invisible forces between atoms are what hold the world together. Neutron stars contain atoms compressed so densely that a teaspoon would weigh 1,000,000,000 tons on Earth. When massive stars die, their cores collapse under gravity with such force that protons and electrons are crushed together, forming neutrons. These neutrons pack together as tightly as the particles in an atomic nucleus, with no empty space between them. The result is a neutron star, an object so dense that all the matter in a mountain range could fit in a space the size of a sugar cube. A neutron star the size of a city might contain more mass than the entire sun. If you could bring a tiny piece of neutron star material to Earth, it would be so heavy it would fall straight through the ground. This extreme density shows what happens when atoms are stripped of their empty space. The universe can take matter and compress it far beyond anything we experience in everyday life. The periodic table organizes atoms by the number of protons in their nucleus from 1 to 118. Hydrogen has 1 proton, helium has 2, carbon has 6, gold has 79. Each element is defined by its number of protons. This number determines everything about how the atom behaves, what other atoms it bonds with, what color it is, whether it's a metal or a gas, how reactive it is. The periodic table arranges elements in rows and columns so that atoms with similar properties line up together. Scientists can look at where an element sits on the table and predict its behavior. The periodic table is like a map of all the different types of atoms that exist, showing the relationships between them. It's one of the most important tools in chemistry, organizing the building blocks of matter in a way that reveals patterns and connections. Radioactive atoms decay by releasing particles, transforming into different elements over time. Not all atoms are stable. Some have too many neutrons, or their nuclei are arranged in ways that can't last forever. These unstable atoms eventually break apart, releasing energy and particles, alpha particles, beta particles, or gamma rays. When this happens, the atom changes. A uranium atom might decay and become a thorium atom. That thorium atom might decay and become radium. This process continues through a chain of transformations until the atom finally reaches a stable form, usually lead. Radioactive decay happens at predictable rates. Some atoms decay in seconds. Others take billions of years. This predictability allows scientists to use radioactive atoms as clocks, measuring the age of rocks, fossils, and ancient artifacts. Even though decay seems destructive, it's just atoms finding their way to stability. Silicon atoms form the basis of sand, glass, and the semiconductor chips in every computer. Silicon is one of the most abundant elements on Earth, found in rocks, soil, and sand. When silicon atoms bond with oxygen atoms, they create silicon dioxide, the main component of sand and quartz. Heat that sand hot enough, and it melts into glass. But silicon has another remarkable property. When it's extremely pure and arranged in perfect crystals, it can conduct electricity in carefully controlled ways. This makes it perfect for computer chips. Engineers can manipulate silicon at the atomic level, adding tiny amounts of other elements to change how electrons flow through it. Modern technology depends on our ability to control the behavior of silicon atoms with incredible precision. Every smartphone, computer, and electronic device contains millions or billions of tiny silicon transistors, all working together because of the properties of this one element. Helium atoms are so light they escape Earth's gravity and drift into space forever. Helium is the second lightest element, just after hydrogen. It's what makes balloons float. Helium is lighter than air, but helium's lightness has another consequence. When helium atoms reach the upper atmosphere, where the air is very thin, some of them are moving fast enough to break free from Earth's gravitational pull completely. They drift away into space and never come back. This means Earth is slowly losing its helium. Unlike other elements that cycle through the environment and eventually return, helium escapes permanently. The helium we have now comes from radioactive decay deep underground, where alpha particles, which are actually helium nuclei, are produced and then capture electrons to become helium atoms. But once helium reaches the surface and eventually the atmosphere, it's gone for good. The attraction between atoms creates the surface tension that allows water striders to walk on water. Water molecules are attracted to each other because of the way their atoms are arranged. The oxygen atom in a water molecule pulls electrons toward itself more strongly than the hydrogen atoms do, creating a slight negative charge on the oxygen side and slight positive charges on the hydrogen side. This makes water molecules stick to each other. The positive side of one molecule attracts the negative side of another. At the surface of water, molecules are pulled toward the other water molecules below and beside them, but not above them, where there's only air. This creates a kind of invisible skin on the water's surface, tension strong enough that small insects can stand on it without breaking through. It's a remarkable example of how atomic scale forces, the way electrons are shared in a molecule, can have visible effects in the world we see. Noble gas atoms rarely bond with other atoms because their electron shells are already complete. The outer electron shell of an atom determines how it behaves. Chemically, most atoms have incomplete outer shells, so they're eager to bond with other atoms to fill those shells. But noble gases, helium, neon, argon, krypton, xenon, and radon, have full outer shells already. They don't need to share or exchange electrons with other atoms. This makes them chemically inert, meaning they rarely react with anything. Noble gases exist as single atoms floating freely, not bonded into molecules. This stability is why helium is used in balloons. It won't react with anything, so it's completely safe. It's why neon glows in signs without changing or degrading. The noble gases are content as they are, complete in themselves, neither giving nor taking from the atoms around them. Isotopes are atoms of the same element with different numbers of neutrons in their nuclei. Every element is defined by how many protons it has. Carbon always has 6 protons. Oxygen always has 8. That never changes. But the number of neutrons can vary. Most carbon atoms have 6 neutrons, giving them a total mass of 12. But some carbon atoms have 7 neutrons, making them carbon-13. Others have 8 neutrons, making them carbon-14. These are all still carbon atoms because they all have 6 protons. They behave almost the same chemically, bonding with other atoms in the same ways. But their different masses can affect how they interact in subtle ways. Carbon-14 is radioactive and decays over time, which is why scientists can use it to date ancient objects. Isotopes remind us that even atoms of the same element can have their own variations, their own stories. Carbon-14 atoms decay at a known rate, allowing scientists to date ancient organic materials. When plants absorb carbon dioxide from the air, they take in both regular carbon-12 and radioactive carbon-14. As long as the plant is alive, it keeps absorbing carbon, maintaining a steady ratio of carbon-14 to carbon-12. But when the plant dies, it stops taking in new carbon. The carbon-14 already inside it starts to decay, slowly transforming into nitrogen-14. This decay happens at a predictable pace. After about 5,700 years, half of the carbon-14 will be gone. After another 5,700 years, half of what remained will be gone. By measuring how much carbon-14 is left in old wood, bone, or fabric, scientists can calculate how long ago the organism died. This technique has helped us determine the age of ancient artifacts, fossils, and archaeological sites, turning atoms into clocks that measure time itself. The glow of neon signs comes from electrons in neon atoms jumping between energy levels. Electrons orbit the nucleus in specific energy levels, like steps on a ladder. Normally, electrons stay in the lowest energy level they can. But when energy is added through electricity, heat, or light, electrons can absorb that energy and jump up to a higher level. They don't stay there long, though. Within a fraction of a second, they fall back down to their original level. When they fall, they release the energy they absorbed as light. The color of that light depends on how far the electron fell and what element the atom belongs to. In neon gas, the electrons release orange-red light. Other elements release different colors. Mercury gives off blue-white, sodium gives off yellow. Every time you see a glowing sign or a street light, you're watching electrons dance between energy levels, releasing tiny bursts of light with each jump. Atoms in a diamond are arranged in a rigid crystalline lattice that makes it Earth's hardest natural material. Each carbon atom in a diamond bonds with 4 other carbon atoms in a 3-dimensional pattern that extends in all directions. These bonds are incredibly strong, and the structure is extremely rigid. There's no way for atoms to slide past each other the way they can in softer materials. This arrangement gives diamonds their hardness. They can scratch almost anything, and only another diamond can scratch them back. Yet diamonds are pure carbon, exactly the same element that makes up soft graphite in pencil lead. The difference is entirely in how the atoms are arranged. The same atoms can create something soft or something hard, something dark or something clear, depending only on their geometry. Structure matters just as much as composition. It's not what you're made of that determines your properties, it's how you're put together. Graphite and diamond are both pure carbon, but only the arrangement of their atoms differs. In graphite, carbon atoms bond together in flat sheets, like stacked pieces of paper. The bonds within each sheet are strong, but the sheets themselves are only weakly connected to each other. This allows the sheets to slide past one another easily, which is why graphite is soft and slippery, perfect for making pencil marks on paper. In diamond, as we've seen, the carbon atoms bond in a rigid 3-dimensional lattice. Same element, completely different structure, completely different properties. This shows how versatile atoms can be. The same building blocks can create an endless variety of materials depending on how they connect. Nature and chemistry are full of these transformations. Silicon and oxygen arrange one way to make sand, another way to make quartz, another way to make opal. The atoms themselves never change, only their relationships change. Nitrogen atoms make up 78% of Earth's atmosphere, cycling through soil, plants, and animals. Most of the air you breathe is nitrogen, but you can't use it directly. Nitrogen gas in the air consists of 2 nitrogen atoms bonded so tightly together that most organisms can't break them apart. Special bacteria in soil and water can split those nitrogen molecules and incorporate the atoms into compounds that plants can absorb. Plants use nitrogen to build proteins and DNA. Animals eat the plants and use that nitrogen for their own proteins. When organisms die and decompose, the nitrogen returns to the soil. Some of it is converted back into nitrogen gas by other bacteria and returns to the atmosphere. This is the nitrogen cycle, a slow movement of atoms from air to soil to life and back again. Every protein in your body contains nitrogen atoms that have been cycling through this process for millions of years, borrowed temporarily from the atmosphere and destined to return. The color of fireworks depends on which metal atoms are heated. When metals are heated to high temperatures, their electrons absorb energy and jump to higher energy levels. When those electrons fall back down, they release light at specific wavelengths that we perceive as colors. Each element releases its own characteristic color. Copper burns blue. Strontium burns red. Sodium burns yellow. Barium burns green. Fireworks makers carefully choose which metal compounds to include in their explosives to create specific colors in the sky. When you watch fireworks, you're watching atoms get excited and release that excitement as colored light. The entire display is a visible demonstration of atomic behavior, electrons jumping and falling, energy transforming into beauty. Chemistry becomes art, and atoms become part of celebration and wonder. Atoms in gases move freely at high speeds. In liquids, they slide past each other. In solids, they vibrate in fixed positions. The state of matter, whether something is a solid, liquid, or gas, depends on how much energy the atoms have and how strongly they're attracted to each other. In solids, atoms are held tightly by bonds. They vibrate in place but can't move around. This gives solids their fixed shape and volume. In liquids, atoms have more energy. They're still attracted to each other, but not strongly enough to hold them in fixed positions. They can slide past one another, which is why liquids flow and take the shape of their container. In gases, atoms have so much energy that they overcome the attractions between them almost entirely. They fly around freely, bouncing off each other and the walls of their container. The same substance can exist in all three states: water, as ice, liquid, and steam, depending only on temperature. The atoms don't change. Only their motion and arrangement change. Phosphorus atoms in your DNA once cycled through ancient oceans, rocks, and countless organisms. Phosphorus is essential for life. It forms the backbone of DNA and RNA, carrying genetic information in every living cell. It's also part of ATP, the molecule that stores and transfers energy in cells. But phosphorus is also relatively rare. Unlike carbon, nitrogen, and oxygen, which cycle through the atmosphere, phosphorus cycles mainly through rocks and water. Rain slowly dissolves phosphorus from rocks and carries it into rivers and oceans. Living things absorb it, use it, and pass it along through food chains. When they die, some phosphorus returns to the soil and water, but some gets locked away in sediments at the bottom of the ocean, where it might remain for millions of years until geological processes bring it back to the surface. The phosphorus atoms in your cells right now have taken this long journey many times. They're ancient travelers moving through deep time. Chlorophyll molecules capture sunlight using magnesium atoms at their center to power photosynthesis. In the heart of every chlorophyll molecule sits a single magnesium atom, surrounded by a ring of carbon and nitrogen atoms. This structure is perfectly designed to absorb light. When sunlight hits the chlorophyll, electrons in the magnesium and surrounding atoms absorb that light energy and become excited. This energy is then used to split water molecules and build sugar molecules from carbon dioxide. Without that magnesium atom, the whole process wouldn't work. Plants wouldn't be able to capture sunlight, and life as we know it would be impossible. It's remarkable that a single atom in the right position can have such enormous consequences. One magnesium atom at the center of a molecule makes the difference between sunlight as wasted energy and sunlight as the fuel for nearly all life on Earth. Salt crystals form perfect cubes because sodium and chlorine atoms arrange in alternating patterns. When sodium and chlorine atoms bond together, they create what's called an ionic bond. The sodium atom gives up one of its electrons to the chlorine atom. This makes the sodium positively charged and the chlorine negatively charged, and opposite charges attract. In a salt crystal, the sodium and chlorine ions arrange themselves in a three-dimensional grid, alternating back and forth in all directions. Each sodium ion is surrounded by chlorine ions, and each chlorine ion is surrounded by sodium ions. This pattern naturally creates a cubic shape. When you look at table salt under a magnifier, you can see tiny cubes. The shape of the crystal reflects the arrangement of atoms inside it. Geometry at the atomic level determines geometry at the scale we can see. The orderly arrangement of atoms creates beauty and pattern, turning invisible forces into visible structure. The copper atoms in pennies and electrical wires were created in supernova explosions billions of years ago. Copper is too heavy to be made in ordinary stars. It requires the intense conditions of a supernova when a massive star explodes at the end of its life. In those brief moments of explosion, atomic nuclei are bombarded with neutrons and transformed into heavier elements. Copper forms in this chaos and is scattered into space along with everything else the star created. Eventually, some of that copper became part of the cloud that formed our solar system. It settled into Earth, concentrated in certain rock formations, and humans discovered it thousands of years ago. We've been using it ever since for tools, coins, plumbing, electrical wiring. The copper conducting electricity through the walls of your house traveled across the galaxy for billions of years before arriving here. Every piece of copper has a cosmic origin. Atoms emit specific wavelengths of light like fingerprints, allowing astronomers to identify elements in distant stars. When atoms are heated or energized, their electrons jump to higher energy levels and then fall back down, releasing light at very specific wavelengths. Each element has its own unique pattern of wavelengths it can emit, like a barcode or fingerprint. Scientists can split light into its component wavelengths using a prism or spectrometer, creating what's called a spectrum. By looking at which wavelengths are present, they can tell exactly which elements are present, even in objects millions or billions of light years away. This is how we know what stars are made of without ever visiting them. We can look at the light from a distant galaxy and identify hydrogen, helium, carbon, oxygen, and all the other elements by their distinctive signatures. Atoms reveal themselves through the light they release, and that light travels across unimaginable distances to tell us their story. Quantum mechanics reveals that electrons don't orbit like planets, but exist as probability clouds around the nucleus. The early models of atoms showed electrons as tiny particles circling the nucleus in fixed paths, like planets around the sun. But as scientists learned more, they realized this picture wasn't quite right. Electrons don't follow definite paths. Instead, they exist in regions around the nucleus where they're likely to be found. These regions are called orbitals, and they have strange shapes. Some are spherical, some are dumbbell-shaped, some are even more complex. An electron in an orbital doesn't have a specific location at any given moment. It exists as a kind of cloud of probability. The cloud is denser where the electron is more likely to be, and fainter where it's less likely. This strange behavior is one of the fundamental mysteries of quantum mechanics. At the atomic scale, certainty gives way to probability, and particles behave in ways that seem impossible in the everyday world we know. The uncertainty principle states we cannot know both an electron's position and momentum simultaneously with perfect precision. This isn't a limitation of our measuring tools. It's a fundamental property of nature. The more precisely you know where an electron is, the less precisely you can know how fast it's moving and in what direction. And the more precisely you know its momentum, the less precisely you can know its location. This principle, discovered by physicist Werner Heisenberg, shows that at the quantum level, the universe has built-in limits to what can be known. Particles like electrons don't have definite positions and speeds the way baseballs or cars do. They exist in a state of inherent uncertainty. This seems strange because it contradicts our everyday experience, but countless experiments have confirmed it's true. The uncertainty principle is one of the foundations of quantum mechanics, reminding us that reality at the smallest scales operates by different rules than the world we can see and touch. Atoms can exist in multiple states simultaneously in quantum superposition until measured. This is one of the strangest features of quantum mechanics. An electron can be in multiple energy states at once, not in one orbital or another, but in both at the same time. A particle can be spinning in two directions simultaneously. These superpositions exist as long as the system is undisturbed. But when you measure the atom or particle, the superposition collapses, and you find it in one definite state. Before the measurement, it genuinely existed in multiple states at once. This behavior has been proven in countless experiments and is the basis for emerging technologies like quantum computers. It's deeply counterintuitive. Our brains evolved to understand the everyday world where things are in one place at a time, in one state at a time. But atoms follow different rules. They inhabit a realm where possibilities coexist until observation forces them to choose. The Pauli exclusion principle prevents electrons from occupying the same quantum state, giving atoms their structure. This principle, named after physicist Wolfgang Pauli, states that no two electrons in an atom can have the exact same set of quantum properties. Each electron must be unique in some way, different energy level, different orbital, or different spin. This rule is why electrons arrange themselves in shells around the nucleus rather than all crowding into the lowest energy state. The first shell can hold only 2 electrons, the second can hold 8, the third can hold 18. As you add more electrons to an atom, they're forced to occupy higher and higher energy levels because the lower ones are already full. This gives each element its unique chemical properties. The exclusion principle is what makes chemistry possible. Without it, all electrons would collapse into the lowest energy state, and atoms would be structurally identical. There would be no variety, no complexity, no molecules, no life. Metallic atoms share their outer electrons in a sea that allows electricity and heat to flow. In metals like copper, iron, or gold, the atoms pack closely together and their outer electrons become delocalized. They're no longer bound to individual atoms but move freely throughout the entire piece of metal. This creates what scientists call an electron sea, a fluid of electrons flowing around fixed atomic nuclei. This is why metals conduct electricity so well. When you apply voltage, the free electrons all drift in the same direction, carrying electric current. It's also why metals conduct heat. Vibrating atoms pass energy to nearby atoms through collisions, and the free electrons carry heat energy quickly throughout the material. And it's why metals are shiny. The free electrons can absorb light and re-emit it easily. The metallic bond, where atoms share electrons collectively rather than pairing up individually, creates a whole class of materials with distinctive properties we've relied on throughout human history. The atoms in your morning coffee have traveled through rain clouds, rivers, and underground aquifers. Water is constantly cycling through the environment. The water you drink today might have been part of a cloud last week, rain on a mountain last month, and part of the ocean last year. Some of it might have flowed through underground rock formations that naturally filter and purify it. Some might have been absorbed by plants and released back into the air through transpiration. The oxygen and hydrogen atoms that make up water molecules are ancient, and they've been on countless journeys before becoming your morning coffee. They've been ice in glaciers, vapor in the air, liquid in rivers and oceans, moisture in soil. Each water molecule carries no memory of where it's been, but the atoms themselves have witnessed ages of planetary history. Drinking a glass of water connects you to the entire hydrological cycle, linking you to every place that water has been. Sulfur atoms give rotten eggs their smell, gunpowder its explosive power, and hot springs their distinctive odor. Sulfur is a yellow element that forms strong-smelling compounds. When proteins containing sulfur break down, they release hydrogen sulfide gas, which smells like rotten eggs. This same gas bubbles up from volcanic hot springs, creating their characteristic odor. Sulfur is also one of the key ingredients in gunpowder, along with carbon and potassium nitrate. When ignited, the sulfur reacts rapidly, releasing heat and gases that create an explosion. Sulfur appears in many places in nature and industry. It's in rubber, matches, fertilizers, and many industrial chemicals. It's essential for life, too, appearing in some amino acids and vitamins. Despite its reputation for unpleasant smells, sulfur is an important element. The atoms themselves are neutral, neither good nor bad. It's only in certain combinations and contexts that they create odors we find unpleasant, reminding us that our reactions to atoms are shaped by biology and chemistry working together. Atoms bond to form molecules when two or more atoms share or exchange electrons. A molecule is simply two or more atoms connected together by chemical bonds. Some molecules are small and simple. Water is just two hydrogen atoms and one oxygen atom bonded together. Others are enormous and complex. A single DNA molecule can contain billions of atoms arranged in a specific sequence. The bonds between atoms can be strong or weak, flexible or rigid. They determine what the molecule looks like, how it behaves, what reactions it can participate in. Everything around you is made of molecules, from the air you breathe to the proteins in your cells. Molecules are how atoms organize themselves into larger structures. A single atom of carbon or hydrogen can't do much on its own. But when atoms connect, when they share their electrons and stabilize each other, they create substances with entirely new properties. Molecules are the next level of organization, atoms cooperating to become something greater than themselves. The age of rocks is measured by comparing ratios of radioactive atoms to their decay products. Some atoms are radioactive, meaning they're unstable, and slowly transform into different atoms over time. This decay happens at a predictable rate. For example, uranium-238 decays into lead-206, and we know it takes about 4.5 billion years for half of any sample of uranium-238 to become lead. By measuring how much uranium and how much lead is in a rock, scientists can calculate how long the decay has been happening, which tells them when the rock formed. Different radioactive atoms decay at different rates, so scientists can choose the right one for dating different ages of rocks. Young rocks might be dated using carbon-14, which decays over thousands of years. Ancient rocks might be dated using uranium or potassium, which decay over billions of years. Atoms become clocks, marking the passage of deep time. Lead atoms are the final stable endpoint when uranium and thorium atoms complete their radioactive decay. Uranium and thorium are heavy, unstable elements. Over millions or billions of years, they decay through a series of transformations, releasing particles and energy along the way. A uranium atom might become thorium, then radium, then radon, then polonium, going through more than a dozen different forms. Eventually, after all those changes, it becomes lead, specifically lead-206 or lead-207, depending on which uranium isotope it started as. Lead is stable. It doesn't decay further. It's the end of the road. This is why lead is found in old rocks alongside uranium. The lead wasn't there when the rock first formed. It's the accumulated result of billions of years of decay. Every lead atom in those rocks used to be something else, uranium or thorium, patiently transforming over unimaginable spans of time until reaching stability. Atoms in the sun's core fuse together under extreme pressure, releasing the energy that lights our days. The sun's core is incredibly hot and dense. Temperatures reach about 15 million degrees Celsius, and the pressure is enormous. Under these conditions, hydrogen atoms move so fast that when they collide, they overcome the electromagnetic repulsion between their nuclei and fuse together. 4 hydrogen nuclei combine to form one helium nucleus. But the helium weighs slightly less than the 4 hydrogen nuclei did. That tiny bit of missing mass is converted into energy according to Einstein's famous equation, E equals mc squared. This fusion reaction releases tremendous amounts of energy, which radiates outward from the sun's core, eventually reaching us as sunlight and heat. Every ray of sunshine that warms your face, every photon that helps plants grow, comes from atoms fusing together at the center of the sun. Stars are fusion reactors, transforming lighter elements into heavier ones and releasing energy in the process. The aluminum atoms in aircraft were created in supernovae and drifted through space for billions of years. Aluminum is element 13, too heavy to be made in ordinary stars, but not so heavy that it requires the most extreme supernova conditions. When a massive star explodes, the shock wave and intense heat create conditions where aluminum nuclei can form. Those aluminum atoms are then scattered into space, along with all the other elements the star created. They drift through the galaxy for millions or billions of years as part of vast clouds of gas and dust. Eventually, some of them become part of new star systems. Some settle into planets. On Earth, aluminum is one of the most abundant elements in the crust, concentrated in rocks like bauxite. Humans learned to extract it and refine it, and now we use it for everything from soda cans to aircraft frames. Every piece of aluminum was once part of an exploding star, and its journey from supernova to airplane is billions of years long. Hydrogen atoms are the simplest atoms, with just one proton and one electron. Hydrogen is element number 1, the first entry in the periodic table, and the most abundant element in the universe. A hydrogen atom has the simplest possible structure. A single proton forms the nucleus, and a single electron orbits around it. That's all. No neutrons, no complex electron shells, just the fundamental pairing of one positive charge and one negative charge. Despite this simplicity, hydrogen is incredibly important. It's the fuel that powers stars through fusion. It's one of the key components of water. It appears in almost every organic molecule. The universe started with mostly hydrogen, formed in the first moments after the Big Bang, and everything heavier was built from it. Hydrogen is where atomic structure begins, the simplest possible arrangement of matter, the foundation upon which all complexity rests. Some atoms are so unstable they exist for only fractions of a second before decaying. Most of the atoms we encounter in daily life are stable. They can exist for billions of years without changing. But scientists have created artificial elements in laboratories by smashing atoms together with enormous energy. Many of these super heavy elements are incredibly unstable. Element 118, oganesson, has a half-life of less than a millisecond. Element 117, tennessine, lasts only a few tens of milliseconds. These atoms form and then immediately fall apart, decaying into lighter elements. They exist just long enough to be detected before they're gone. Creating and studying these fleeting atoms helps scientists understand the forces that hold nuclei together and the limits of how large and heavy an atom can be. Even though these atoms are short-lived, they're still real. They follow the same rules as stable atoms, just pushed to an extreme where stability becomes impossible. The atoms in amber trapped insects and tree resin together, preserving both for millions of years. Amber is fossilized tree resin. Millions of years ago, trees produced sticky resin to protect themselves from damage or infection. Sometimes insects or other small creatures got caught in that resin. As more resin flowed, it covered them completely. Over millions of years, buried underground, the resin hardened and fossilized, becoming amber. The atoms in the amber arranged themselves into stable structures that resist decay. The insects inside were sealed away from air and moisture, protected from decomposition. The result is fossils of incredible detail. You can see individual hairs, wings, even cells preserved exactly as they were millions of years ago. The atoms in the amber haven't changed much. They've just rearranged slightly, becoming harder and more stable while keeping their structure intact. Amber is atoms doing what they do best, persisting, enduring, holding their form across spans of time that dwarf human history. Mercury atoms are unusual because mercury is the only metal that's liquid at room temperature. Most metals are solid. Think of iron, copper, gold, aluminum. They're atoms packed together in rigid structures that give metals their characteristic hardness. But mercury is different. The way mercury atoms interact with each other is unusual. The bonds between them are weak enough that at room temperature, the atoms can slide past each other freely, making mercury a liquid. It's dense and silvery, flowing like water, but much heavier. Mercury has been known since ancient times, fascinating people with its strange properties. It's useful in thermometers and barometers because it expands and contracts predictably with temperature and pressure. But it's also toxic. Mercury atoms can interfere with biological processes if they get into your body. Mercury reminds us that even among metals, which generally behave similarly, individual elements can have their own unique quirks based on how their atoms are structured. Atoms in your fingernails grow slowly outward, incorporating new atoms from proteins you've eaten. Your fingernails are made mostly of a protein called keratin. As your body produces new keratin molecules at the base of your nail, the older keratin is pushed outward. The atoms that make up those keratin molecules, carbon, nitrogen, hydrogen, oxygen, and sulfur, come from the food you eat. Your body breaks down proteins in your diet, releases the amino acids, and then reassembles them into new proteins like keratin. The atoms that form your fingernails today were in your food a few weeks or months ago. They might have been part of plants, animals, or grains. Now they're part of you, temporarily organized into the structure of a fingernail. Eventually, you'll trim your nails, and those atoms will be released back into the environment. Everything flows, atoms come in, serve their purpose, and move on. Your body is constantly rebuilding itself from whatever atoms are available, creating the illusion of permanence from materials that are always changing. Radon atoms form naturally from uranium decay in rocks and can accumulate in basements. Uranium is found in small amounts in many rocks and soils. As uranium atoms decay, they go through a series of transformations, eventually producing radon, a radioactive noble gas. Because radon is a gas, it can seep out of rocks and soil and move through tiny cracks and gaps. If a building is built on ground containing uranium-bearing rocks, radon can accumulate inside, especially in basements and lower floors where ventilation is limited. Radon itself is radioactive and decays further, releasing particles that can be harmful if breathed in over long periods. But radon atoms don't last long. They have a half-life of just a few days before decaying into other elements. Testing for radon is simple, and proper ventilation can reduce any accumulation. This is atoms in motion, moving from solid rock into the air we breathe, connecting geology to the spaces we inhabit. The spacing between atoms determines whether a substance is a solid, liquid, or gas. Temperature affects how much energy atoms have, and that energy determines how they move. In a solid, atoms are packed closely together and held by strong bonds. They vibrate but stay in place. In a liquid, atoms have more energy. The spacing between them increases slightly, and the bonds become looser, allowing atoms to slide past each other. In a gas, atoms have so much energy that they break free from their neighbors almost completely. The spacing between gas atoms is much larger than in solids or liquids. Air, for example, is mostly empty space with atoms scattered far apart, moving at high speeds. The same substance can transition between these states. Ice melts into water. Water evaporates into steam, simply by changing how much energy the atoms have. The atoms themselves don't change, only the distances between them and the strength of their interactions. Argon atoms fill light bulbs to prevent the tungsten filament atoms from evaporating too quickly. When an electric current passes through the tungsten filament in a light bulb, it heats up to thousands of degrees, hot enough to glow and produce light. But at these temperatures, tungsten atoms can evaporate, breaking free from the solid filament and drifting away. This gradually makes the filament thinner until it breaks. To slow this process, manufacturers fill light bulbs with argon gas. Argon is a noble gas. It doesn't react with tungsten or any other atoms, but its presence creates pressure that reduces the rate at which tungsten atoms evaporate. The argon atoms just sit there, doing nothing chemically, but their physical presence extends the life of the bulb. It's a simple solution using the inertness of noble gas atoms to protect the filament. Without argon, light bulbs would burn out much faster, filaments disappearing atom by atom into the surrounding vacuum. The atoms in glass flow extremely slowly over centuries, making old window panes slightly thicker at the bottom. This is a common story, though scientists debate how accurate it is. Glass is sometimes called a supercooled liquid because its atoms are not arranged in a regular crystalline pattern the way they are in most solids. Instead, glass atoms are somewhat randomly arranged, more like a liquid that's been frozen in place. Some people have noticed that very old window panes in medieval buildings are thicker at the bottom than the top, and suggested this means glass flows downward over centuries. Scientists now think this thickness variation is more likely due to how glass was manufactured in the past rather than flow, but glass does have unusual properties. Its atoms are locked in place but not in a perfectly ordered structure. Over extremely long time scales, there might be some very slow rearrangement. Whether or not old windows prove it, glass reminds us that the boundary between solid and liquid isn't always sharp. Some materials exist in between, with atoms that are neither fully mobile nor fully fixed. Iodine atoms are essential for thyroid hormone production in animal bodies. The thyroid gland, a small organ in your neck, produces hormones that regulate metabolism, growth, and energy use throughout your body. To make these hormones, the thyroid needs iodine. Each thyroid hormone molecule contains 3 or 4 iodine atoms attached to a protein structure. Without enough iodine, your thyroid can't produce enough hormone, leading to health problems. Humans get iodine from food. It's naturally present in seafood, dairy products, and some plants, and it's added to table salt in many countries. The iodine atoms you consume today might have been in the ocean last year, absorbed by seaweed or fish, then harvested and processed. Eventually, they reach your thyroid, where they're incorporated into molecules that help control how your cells use energy. A few atoms of one element in the right place can have profound effects on health and well-being. Biology depends on chemistry, and chemistry depends on atoms being where they need to be. Atoms in meteorites formed in different stellar environments than Earth's atoms, revealing their cosmic origins. When scientists analyze meteorites, rocks that fall from space and land on Earth, they find something fascinating. The ratios of different isotopes in meteorite atoms don't quite match the ratios in Earth rocks. This tells us that meteorite material formed in different parts of the early solar system, or even in different stars, than the material that became Earth. Some meteorites contain tiny grains that are older than the solar system itself, preserved since before the sun formed. These pre-solar grains have isotope ratios that identify them as coming from specific types of stars. By studying the atoms in meteorites, scientists can reconstruct the history of the early solar system and learn about the stars that existed before it. Every atom carries information about its origin in its structure, in the number of neutrons it has, in how it interacts with other atoms. Atoms are archives, storing cosmic history. The covalent bonds between atoms share electrons, creating molecules stronger than ionic bonds. There are different ways atoms can bond together. In an ionic bond, one atom gives an electron to another atom, creating charged ions that attract each other. These bonds can be strong, but they can also be broken fairly easily when dissolved in water. In a covalent bond, atoms share electrons between them. The shared electrons spend time orbiting both nuclei, effectively gluing the atoms together. Covalent bonds tend to be stronger and more stable than ionic bonds. They're what hold together the molecules that make up most organic compounds, including proteins, DNA, fats, and carbohydrates. The strength of covalent bonds is why diamond is so hard. Each carbon atom shares electrons with 4 neighbors in a 3-dimensional network of covalent bonds. Breaking these bonds requires enormous energy. The way atoms share their electrons determines not just what molecules form, but how strong and stable those molecules are. Covalent bonds are atoms cooperating, sharing resources, creating structures that neither could form alone. Fluorine atoms bond so readily with other atoms that pure fluorine must be stored in special containers. Fluorine is the most reactive element on the periodic table. Its atoms have 7 electrons in their outer shell and desperately want one more to complete the shell. This makes fluorine extremely eager to grab electrons from other atoms. Fluorine reacts violently with almost everything: metals, nonmetals, even noble gases under the right conditions. Pure fluorine gas is so reactive that it attacks glass, many plastics, and most metals, making it difficult to store. Special containers made of certain alloys or nickel can resist fluorine's reactivity. Despite its danger in pure form, fluorine compounds are remarkably stable and useful. Fluoride in toothpaste helps protect teeth. Teflon, a fluorine-containing polymer, creates non-stick surfaces. Fluorine's extreme reactivity means that once it bonds with something, it tends to stay bonded. The same property that makes elemental fluorine dangerous makes fluorine compounds incredibly stable. The atoms in glacial ice trap ancient air bubbles, preserving atmospheric history for hundreds of thousands of years. When snow falls and accumulates in places like Antarctica or Greenland, it slowly compresses into ice. As layers of snow are buried under new snowfall, the spaces between snowflakes become isolated pockets of air that get sealed into the ice. These air bubbles contain a sample of the atmosphere from when that snow fell. Oxygen, nitrogen, carbon dioxide, and trace gases, all in the proportions that existed at that time. Scientists can drill deep into ice sheets, extracting cores that go back hundreds of thousands of years. By analyzing the air bubbles at different depths, they can measure how the atmosphere has changed over time, how much carbon dioxide there was during ice ages versus warm periods, how methane levels varied, how temperature and atmospheric composition are related. The atoms in those bubbles have been sealed away, unchanged, waiting to tell their story. Ice cores are time capsules with atoms of ancient air preserved perfectly, connecting us to climates and atmospheres from long before human civilization began. Sodium atoms react violently with water, releasing hydrogen gas and heat. Sodium is a soft, silvery metal that's extremely reactive. If you drop a piece of sodium into water, it immediately starts reacting. The sodium atoms give up their outer electrons to water molecules, breaking the water apart. This produces sodium hydroxide, a strong base, and hydrogen gas. The reaction releases so much heat that the hydrogen gas often ignites, creating a small flame that dances across the surface of the water. Larger pieces of sodium can explode when dropped in water. This violence comes from how badly sodium atoms want to get rid of their single outer electron. Once that electron is gone, the sodium atom becomes a positively charged ion with a complete, stable electron shell. It's satisfied. The energy released in achieving that stability is what powers the reaction. Pure sodium is never found in nature because it reacts with moisture in the air immediately. All natural sodium exists as compounds: sodium chloride in salt, sodium carbonate in minerals. The pure metal exists only when humans extract it and keep it isolated from water and air. The atoms in coal represent ancient forests compressed and heated over millions of years. Hundreds of millions of years ago, during the Carboniferous period, vast forests covered much of the earth. When trees and plants died, they fell into swamps where they were buried under layers of sediment before they could fully decompose. Over time, as more and more layers piled on top, the plant material was compressed and heated. The pressure and heat drove out moisture and gases, concentrating the carbon atoms that made up the original plants. First, this created peat, then lignite, then harder coal. The carbon atoms in coal are the same atoms that were once part of living trees, capturing sunlight through photosynthesis, building wood and leaves. Now those atoms are locked underground, concentrated energy from ancient sunshine. When we burn coal, we're releasing energy that was stored by plants millions of years ago, returning carbon atoms to the atmosphere where they can begin the cycle again. Coal is fossilized sunlight, atoms transformed by time and pressure. Helium atoms were named after Helios, the Greek sun god, because they were first discovered in the sun's spectrum. In the mid-1800s, scientists learned to study the light from the sun by splitting it into its component wavelengths. They noticed certain dark lines in the spectrum where specific wavelengths were absorbed. Each element creates its own unique pattern of lines. Most of the lines matched known elements like hydrogen, sodium, and iron. But in 1868, astronomers noticed a set of yellow lines that didn't match any element known on Earth. They concluded this must be a new element and named it helium, after Helios, the sun. It wasn't until decades later that helium was discovered on Earth, isolated from uranium-bearing minerals where it's produced by radioactive decay. For years, helium was an element we knew existed only because we could see its signature in sunlight. The atoms revealed themselves through the light they absorbed, proving their existence across 93 million miles of space before anyone found them here at home. The atoms in your teeth enamel are arranged in a hydroxyapatite crystal structure that makes them incredibly hard. Tooth enamel is the hardest substance in the human body. It's made primarily of a mineral called hydroxyapatite, which consists of calcium, phosphorus, and oxygen atoms arranged in a specific crystalline pattern. This structure gives enamel its strength and resistance to wear. The crystals are packed tightly together, creating a surface that can withstand the forces of chewing for decades. But enamel is also slightly porous at the microscopic level, which is why acids from food or bacteria can gradually dissolve it, causing cavities. Fluoride helps protect teeth because fluoride atoms can replace some of the hydroxide groups in hydroxyapatite, creating fluorapatite, which is even more resistant to acid. The atoms in your teeth are constantly exchanging with atoms in your saliva, absorbing minerals to repair tiny damage, and losing minerals when acid is present. Your teeth are dynamic structures, atoms arranged in hard crystals but still participating in chemistry. Plutonium atoms don't exist naturally on Earth anymore because they decay too quickly and must be created artificially. When Earth formed 4.5 billion years ago, it likely contained some plutonium atoms created in supernovae. But plutonium is radioactive and decays relatively quickly on geological timescales. The most stable plutonium isotope has a half-life of about 80 million years. After billions of years, any primordial plutonium has long since decayed into other elements. The plutonium that exists today is created artificially in nuclear reactors. When uranium atoms in a reactor are hit by neutrons, some of them absorb those neutrons and transform into plutonium. Humans have created tons of plutonium this way for nuclear weapons and reactor fuel. It's strange to think that there are atoms in the world today that didn't exist naturally on Earth for billions of years, brought back into existence only through human technology. Plutonium atoms remind us that the inventory of elements on Earth changes over time. Some disappear through decay. Others can be created if we know how to arrange the right nuclear reactions. The electromagnetic repulsion between atoms prevents solid objects from passing through each other. When you set a book on a table, you might think the book is resting on the table's surface with the atoms touching. But atoms never actually touch. What's really happening is that the electrons in the atoms at the bottom of the book are repelling the electrons in the atoms at the top of the table. Both sets of electrons have negative charges, and negative charges push each other away. The closer the electrons get, the stronger the repulsion. The table pushes up on the book with exactly enough force to balance the downward pull of gravity. This electromagnetic repulsion is what we experience as solidity and support. If electromagnetic forces suddenly vanished, the book would fall through the table as if it weren't there. The table would collapse. Everything would lose its structure. The fact that you can stand on the floor, hold an object, or sit in a chair, all of that depends on atoms repelling each other through electromagnetic forces, maintaining distances that feel solid to us but are actually just balanced forces. Carbon atoms form long chains easily, making them the foundation of all organic molecules and life. Carbon's atomic structure, with 4 electrons in its outer shell, allows it to bond with 4 other atoms simultaneously. These bonds can connect to other carbon atoms, creating chains, branches, and rings of virtually unlimited length and complexity. Carbon can bond with hydrogen to make hydrocarbons. It can bond with oxygen to make carbohydrates and carbon dioxide. It can bond with nitrogen to make amino acids and DNA. This versatility makes carbon uniquely suited for creating the complex molecules life requires. Every living thing on Earth is built primarily from carbon-based molecules, proteins, DNA, cell membranes, hormones, vitamins. They're all organic molecules with carbon skeletons. Silicon, which is right below carbon on the periodic table, can also form 4 bonds and create chains, but silicon-silicon bonds are weaker and less stable than carbon-carbon bonds. Carbon is special, not just common, but perfectly suited for complexity. Life as we know it is chemistry based on carbon's unique bonding abilities. The atoms in volcanic lava were once deep in Earth's mantle, cycling upward over millions of years. The Earth's interior is hot and under tremendous pressure. Deep in the mantle, atoms exist in molten rock that flows very slowly in giant convection currents. Hot material rises from near the core, spreads out under the crust, cools, and sinks back down. This process takes millions of years. Sometimes, rising magma finds weak spots in the crust, places where tectonic plates are spreading apart or where a plume of especially hot material pushes upward. The magma forces its way toward the surface, and when it breaks through, it erupts as lava. The atoms in that lava have made a long journey from deep underground to the surface. Once exposed to air, the lava cools and solidifies into new rock. Those atoms become part of the crust. Eventually, through the slow movement of tectonic plates, they might be pushed back down into the mantle again to begin the cycle anew. The atoms in volcanic rock have been recycling through Earth's interior for billions of years, surfacing periodically in dramatic eruptions before returning to the depths. Xenon atoms are so heavy and unreactive, they're used in spacecraft ion engines. Xenon is a noble gas like helium and argon, but much heavier. It has 54 protons and is one of the densest gases. Because it's a noble gas, xenon doesn't react chemically with other elements. This makes it ideal for certain specialized uses. In ion engines for spacecraft, xenon atoms are electrically charged to create ions, then accelerated to very high speeds and expelled from the engine. This creates thrust through Newton's third law. As xenon ions shoot out one direction, the spacecraft is pushed in the opposite direction. Ion engines produce very little thrust compared to chemical rockets, but they can run for years, gradually accelerating a spacecraft to very high speeds using minimal fuel. Xenon is chosen because it's heavy, which means more momentum per atom expelled, and because it's inert, so it won't corrode or react with the engine components. These engines have powered several deep space missions, pushing spacecraft across the solar system atom by atom, xenon ions streaming out into the vacuum of space. The atoms in quartz crystals vibrate at precise frequencies, making them useful for keeping time in watches. Quartz is silicon dioxide, silicon and oxygen atoms arranged in a repeating crystalline pattern. This crystal has a remarkable property. When you squeeze it, it generates a small electrical voltage. This is called the piezoelectric effect. The reverse is also true. If you apply a voltage to quartz, it vibrates. And because the crystal structure is so regular, it vibrates at a very specific, consistent frequency. In a quartz watch, a tiny quartz crystal is connected to a battery. The battery sends electrical pulses to the crystal, making it vibrate at exactly 32,768 times per second. Electronic circuits count these vibrations and use them to advance the watch by 1 second for every 32,768 vibrations. This method is so reliable that quartz watches can keep time to within seconds per month. The atoms in the crystal vibrate with mechanical precision, turning atomic scale motion into something we use every day: accurate time. Lithium atoms in batteries store and release energy by moving between electrodes. A lithium-ion battery contains 2 electrodes, an anode and a cathode separated by an electrolyte. During charging, lithium atoms at the cathode release their outer electrons. The electrons flow through the external circuit to the anode, while the lithium ions move through the electrolyte to the anode, where they recombine with electrons and are stored. When you use the battery, the process reverses. Lithium atoms at the anode release electrons, which flow through your device, powering it, while lithium ions move back to the cathode through the electrolyte. The battery is just facilitating the back and forth movement of lithium atoms and their electrons. Lithium is chosen because it's very light and can hold a lot of energy for its weight. Each lithium atom has just 3 protons, making it one of the lightest metals. Modern life depends on these tiny atoms shuttling back and forth inside billions of devices: phones, laptops, electric cars, storing and releasing electrical energy on demand. The atoms in pearls form in layers as oysters coat irritating particles with calcium carbonate. When a grain of sand or another small particle gets inside an oyster's shell, it irritates the soft tissue inside. To protect itself, the oyster secretes a substance called nacre, also known as mother of pearl. Nacre is made of calcium carbonate, the same material as the oyster's shell, arranged in microscopic layers with organic proteins between them. The oyster deposits layer after layer of nacre around the irritating particle, gradually building up a pearl. This process can take several years. Each layer is incredibly thin, but together they create the smooth, lustrous surface we associate with pearls. The atoms in a pearl are arranged in a crystalline structure that reflects light in beautiful ways, creating the pearl's characteristic shine. Natural pearls are rare because most irritants either get expelled by the oyster or don't trigger the nacre production response. A pearl is patience made visible, atoms deposited slowly, layer by layer, transforming irritation into beauty. Barium atoms give off green light when heated, used in fireworks and emergency flares. Barium is a soft, silvery metal that reacts readily with oxygen. When barium compounds are heated to high temperatures, the energy causes electrons in barium atoms to jump to higher energy levels. When those electrons fall back down, they release energy as light. Barium's particular atomic structure means that much of this light is in the green part of the spectrum. Fireworks makers use barium compounds to create brilliant green explosions in the night sky. Green emergency flares also contain barium for the same reason. The intensity and purity of the color make it easy to see from long distances. Every time you see green in a fireworks display, you're watching barium atoms absorbing heat energy and releasing it as green light. The same atoms that sit stable and quiet in rocks deep underground can, when given energy, put on a spectacular light show. Chemistry is the art of knowing which atoms do what and how to coax them into revealing their properties. The atoms in crude oil represent ancient marine organisms that died and decomposed over millions of years. Oil didn't form from dinosaurs, as popular myth suggests, but from tiny marine organisms, plankton, algae, and bacteria that lived in ancient oceans. When these organisms died, they sank to the ocean floor and were buried under layers of sediment. Over millions of years, as more sediment piled on top, the organic material was subjected to increasing heat and pressure. Chemical reactions broke down the complex organic molecules in the dead organisms, transforming them into simpler hydrocarbon molecules, chains of carbon and hydrogen atoms. This process created crude oil and natural gas. The atoms in oil are the same atoms that were once part of living cells, capturing energy from the sun through photosynthesis or consuming other organisms. Now those atoms exist as fossil fuels, concentrated energy stored underground. When we extract and burn oil, we're releasing energy that was captured by living things in ancient seas. Noble gases like neon and argon exist as single atoms rather than bonding into molecules. Most elements prefer to bond with other atoms. Oxygen exists as O2 molecules, two oxygen atoms bonded together. Nitrogen exists as N2. Even hydrogen normally exists as H2. But the noble gases, helium, neon, argon, krypton, xenon, and radon, don't bond with themselves or, under normal conditions, with other elements. They exist as lone, unbonded atoms drifting through space. This is because their electron shells are complete. They don't need to share or exchange electrons to achieve stability. They are already stable on their own. This chemical inertness makes noble gases useful for applications where you don't want chemical reactions to occur. Helium is used in balloons. Argon fills light bulbs and is used as a protective atmosphere in welding. Neon glows in signs. All these applications take advantage of atoms that are content to remain alone, not seeking partnerships, stable in their solitude. The atoms in rust form when iron atoms bond with oxygen atoms in the presence of water. Rust is iron oxide, the result of iron slowly reacting with oxygen. This reaction happens faster when water is present because water helps facilitate the transfer of electrons. Iron atoms give up electrons, becoming positively charged iron ions. Oxygen atoms accept those electrons, becoming negatively charged oxide ions. The ions attract each other and bond together, forming iron oxide, rust. This process gradually converts solid iron into a flaky, reddish-brown substance. Rust is weaker than iron and takes up more space, which is why rusted metal appears to crumble and expand. The atoms haven't disappeared. They've just rearranged themselves into a different compound with different properties. Rust is iron's slow transformation, atoms finding new partners and new structures. Preventing rust means keeping iron, oxygen, and water apart. Paint, oil, or other coatings act as barriers that prevent the atoms from reaching each other and reacting. Phosphorescent atoms absorb light energy and release it slowly over time, creating glow-in-the-dark effects. Some materials contain atoms that can absorb light energy and hold on to it for a while before releasing it. When light hits these atoms, electrons jump to higher energy levels and get temporarily trapped there. They don't fall back down immediately. Instead, they slowly trickle back to lower levels over minutes or hours. releasing their energy as light along the way. This is phosphorescence. Glow-in-the-dark toys, watch dials, and safety signs use phosphorescent materials. You charge them by exposing them to light, and they glow in the dark. As the trapped energy is gradually released, the atoms are essentially storing light energy and releasing it slowly. This is different from fluorescence, where atoms absorb and immediately re-emit light. Phosphorescence is delayed, patient. The atoms hold on to the energy they received, releasing it bit by bit when darkness falls. It's a reminder that atoms can act as tiny batteries, storing energy in the arrangement of their electrons. The atoms in champagne bubbles are carbon dioxide that was dissolved under pressure. Carbon dioxide dissolves in water and other liquids. During the fermentation process that creates champagne, yeast converts sugar into alcohol and carbon dioxide. In a sealed champagne bottle, the carbon dioxide can't escape, so it dissolves into the liquid under pressure. The bottle might contain several atmospheres of pressure. When you open the bottle, the pressure drops suddenly. The carbon dioxide that was dissolved can no longer stay in solution. It becomes a gas again. Carbon dioxide atoms pair up into molecules and form tiny bubbles that rise to the surface. That's the fizz in champagne, the sparkle in sparkling water, the bubbles in soda. Each bubble is a small pocket of carbon dioxide molecules, atoms of carbon and oxygen bonded together, rising through the liquid and escaping into the air. The same atoms that were trapped in liquid moments ago are now free gas, expanding and rising, released from confinement. Titanium atoms resist corrosion so well that titanium metal can last for centuries underwater. Titanium is a remarkable metal. When exposed to air or water, titanium atoms at the surface immediately react with oxygen to form a thin layer of titanium dioxide. This oxide layer is incredibly stable and protective. It bonds so tightly to the titanium underneath that it prevents further oxidation. Unlike iron oxide, which is flaky and porous, titanium dioxide forms a continuous barrier. The atoms in this barrier don't want to react further. They've already found stable configurations and their content. This makes titanium extremely resistant to corrosion. It doesn't rust in seawater, doesn't degrade in most acids, and can withstand harsh conditions for decades or centuries without significant damage. Titanium is used in aircraft, spacecraft, medical implants, and high-end sporting equipment precisely because it's so durable. The atoms form a protective shield that preserves the metal beneath, making titanium one of the longest-lasting materials we have. The atoms in your brain form connections that encode your memories and thoughts. Your brain contains about 86 billion neurons, cells specialized for transmitting electrical and chemical signals. Each neuron connects to thousands of other neurons through structures called synapses. When you learn something new or form a memory, specific patterns of neurons become linked. The strength of connections between neurons changes based on how often they fire together. This is accomplished through changes at the atomic and molecular level. Neurotransmitter molecules are released, receptor proteins change shape, new proteins are synthesized, and the physical structure of synapses is modified. All of this happens because atoms are rearranging, bonding, and releasing. The atoms in your brain, carbon, hydrogen, oxygen, nitrogen, phosphorus, are constantly moving, reacting, and reorganizing as you think, remember, and experience the world. Your thoughts are patterns of atomic activity, electricity flowing through networks of atoms, chemical signals crossing microscopic gaps. Consciousness emerges from chemistry. You are atoms arranged in ways that allow them to think about themselves. Atoms in superconductors allow electricity to flow without resistance at extremely cold temperatures. In normal materials, when electricity flows, the moving electrons collide with atoms in the material, creating resistance and generating heat. But in certain materials cooled to temperatures near absolute zero, something remarkable happens. Electrons pair up and move through the material in a coordinated way that avoids collisions. The atoms in the material vibrate less because of the extreme cold, and the electron pairs navigate the atomic lattice without resistance. Electricity flows without any energy loss. This is superconductivity. Superconducting materials can carry enormous electrical currents without heating up. They can create powerful magnetic fields. Scientists are working to develop superconductors that work at higher temperatures, which would revolutionize power transmission and electronics. At the coldest temperatures, atoms become so still, so organized, that electrons can slip through them like ghosts, unimpeded, perfect conductors in a near-perfect atomic arrangement. The atoms in opal reflect light in ways that create rainbow colors through diffraction. Opal is a unique gemstone made of silicon dioxide, the same material as quartz and glass, but with a special structure. Inside opal, tiny spheres of silicon dioxide are arranged in regular, repeating patterns. These spheres are all about the same size, roughly the same scale as the wavelength of visible light. When light enters the opal and passes by these spheres, it bends and scatters. Different wavelengths of light bend by different amounts, separating into colors. As you move the opal or change your viewing angle, different colors become visible. This is called diffraction. The rainbow effect in opal doesn't come from pigments or chemicals, but from the physical arrangement of atoms in repeating structures. The atoms are organized with such precision that they act like natural gratings, splitting white light into its component colors. Each opal is unique because the patterns of spheres vary slightly, creating different color displays. It's geometry and physics working together at the atomic level to create beauty. Krypton atoms are used in high-powered lasers and specialized photographic flash lamps. Krypton is another noble gas, heavier than argon, but lighter than xenane. Like all noble gases, it doesn't react chemically with other elements under normal conditions, but krypton has useful properties when electricity passes through it. Krypton atoms can absorb electrical energy and emit bright white light with high efficiency. This makes krypton useful in flash lamps for high-speed photography and in certain types of lasers. Krypton fluoride lasers, which use a mixture of krypton and fluorine gases, produce powerful ultraviolet light used in scientific research and manufacturing. The atoms don't bond permanently. Fluorine and krypton only interact temporarily when energized, but that brief interaction creates useful laser light. Krypton also appears in energy-efficient windows, where it's sealed between glass panes as insulation. The atoms just sit there, not conducting heat well, helping keep buildings warm in winter and cool in summer. Noble gas atoms find their uses not through chemistry, but through their physical properties. The atoms in marble were once limestone, transformed by heat and pressure deep underground. Limestone is a sedimentary rock made mostly of calcium carbonate. It forms from the shells and skeletons of ancient sea creatures that accumulated on ocean floors and were compressed into rock. But when limestone is buried deep underground and subjected to intense heat and pressure, conditions called metamorphism, its structure changes. The calcium carbonate atoms rearrange themselves into larger interlocking crystals. The rock becomes harder denser, and capable of being polished to a smooth shine. This transformed limestone is marble. The atoms are still calcium, carbon, and oxygen, just as they were in the original limestone. But they're organized differently now, packed more tightly, arranged in ways that give marble its strength and beauty. Sculptures and buildings made from marble are really made from the fossilized remains of ancient sea life, atoms that have been on a journey from living organism to seafloor sediment to buried rock to metamorphic stone. Chlorine atoms purify swimming pools and drinking water by disrupting bacterial cell walls. Chlorine is a highly reactive element. When dissolved in water as chlorine gas, hypochlorous acid, or hypochlorite ions, chlorine atoms seek out electrons. Bacteria and other microorganisms have proteins and enzymes on their cell walls and inside their cells. When chlorine encounters these microorganisms, chlorine atoms react with the proteins, breaking chemical bonds and disrupting the structure of essential molecules. This damages the cell walls and interferes with the organism's ability to function, killing them. The same process works on viruses and other pathogens. That's why chlorine is so effective at purifying water. A small amount of chlorine, just a few atoms per million water molecules, is enough to make water safe to drink or swim in. The chlorine atoms do their work and then usually bond with other materials in the water or evaporate. Water treatment is essentially using the reactivity of atoms to protect human health, harnessing chemistry to destroy harmful microorganisms before they can harm us. The atoms in honey can remain stable and edible for thousands of years in sealed containers. Honey is remarkable for its longevity. Archaeologists have found pots of honey in ancient Egyptian tombs that are thousands of years old and still perfectly edible. Several factors contribute to this. Honey is mostly sugar and very little water. Most bacteria and molds need water to grow, and there isn't enough water in honey for them to survive. Honey is also acidic, with a pH around 3.9, which further discourages microbial growth, and bees add an enzyme that produces small amounts of hydrogen peroxide, which has antibacterial properties. The atoms in honey, carbon, hydrogen, and oxygen, mostly, are arranged in sugar molecules that are chemically stable. They don't spontaneously break down or react with each other. As long as honey is sealed away from moisture, it can last indefinitely. The atoms remain patiently in their molecular arrangements, preserving sweetness across centuries, a testament to both the chemistry of sugar and the remarkable process by which bees create this unique food. Uranium atoms split in nuclear fission, releasing tremendous energy and creating lighter elements. Uranium-235 is a heavy, unstable isotope. When a uranium nucleus is hit by a neutron, it absorbs the neutron and becomes even more unstable. The nucleus can't hold itself together and splits apart into two lighter nuclei, often barium and krypton, though other combinations are possible. This splitting releases energy because the two smaller nuclei together weigh slightly less than the original uranium nucleus. That missing mass becomes energy according to Einstein's equation. Fission also releases 2 or 3 additional neutrons. These neutrons can hit other uranium nuclei, causing them to split, releasing more neutrons, creating a chain reaction. If controlled, as in a nuclear reactor, this chain reaction can produce steady energy for electricity. If uncontrolled, as in a nuclear weapon, it releases enormous amounts of energy all at once. Nuclear fission demonstrates that atoms can be broken apart and that doing so releases energy locked in the nucleus. The same forces that hold nuclei together, when overcome, release that binding energy in spectacular fashion. The atoms in snowflakes arrange in hexagonal patterns as water molecules freeze. When water vapor in the atmosphere freezes, water molecules, each one made of 2 hydrogen atoms and 1 oxygen atom, bond together in a crystalline structure. The shape of the water molecule and the way hydrogen bonds form between molecules naturally create hexagonal symmetry. Every snowflake has 6 sides or 6 branches because of this atomic level geometry. As a snowflake forms and falls through the air, it encounters different temperatures and humidity levels. These conditions affect how water molecules are added to the growing crystal. Slight variations in conditions create the intricate, unique patterns we associate with snowflakes. But the 6-fold symmetry is always present because that's determined by how water molecules bond at the atomic level. No 2 snowflakes are likely to be identical because each one experiences a slightly different journey through the atmosphere, but they all share the same basic hexagonal structure, a visible expression of atomic geometry, proof that the smallest scales of organization influence the shapes we see in the world. Cobalt atoms give blue glass and ceramics their distinctive color. When cobalt oxide is added to glass or ceramic glazes, the cobalt atoms become part of the material's structure. Cobalt has unpaired electrons in its atomic structure. These electrons can absorb certain wavelengths of visible light, specifically wavelengths in the orange and red parts of the spectrum. When white light passes through or reflects off cobalt-containing glass, the orange and red light is absorbed, and the remaining light, blues and violets, passes through or reflects back to our eyes. This is why cobalt glass appears deep blue. The effect is so strong that only small amounts of cobalt are needed. A few cobalt atoms per 1,000 atoms of glass are enough to create vivid blue coloring. Ancient civilizations discovered this property thousands of years ago and used cobalt to create blue pottery and decorative glass. Modern ceramics still use cobalt for blue decoration. The color comes entirely from how cobalt atoms interact with light at the atomic level. No dyes, no pigments in the traditional sense, just atoms with electron configurations that selectively absorb certain colors and transmit others. The atoms surrounding you right now will continue their patient existence long after you and everything you know has transformed into something new. Atoms don't die, they don't wear out. The carbon atom that's part of your body today might have been part of a tree a century ago, part of the soil before that, part of an animal before that, going back through an unbroken chain of transformations for billions of years. After you, that atom will become part of something else, released when you exhale, returned to the earth when you eventually die, absorbed by plants, eaten by animals, cycling endlessly through the world. The same is true for every atom around you. The atoms in the walls, in the air, in the ground beneath you, they've been here for eons and will be here for eons more. They're recycled endlessly through the universe's long, slow turning. Mountains erode and become soil. Soil nourishes plants that become animals that die and decompose and return to soil. Everything flows, everything transforms, but the atoms themselves persist, patient and eternal, moving from form to form without beginning or end. You are a temporary arrangement of ancient atoms, and when this arrangement dissolves, those atoms will move on to new arrangements, new forms, new stories, continuing their infinite journey through time and space.